Good morning, sir. I'm Kevanela. My roll number is 25955A6626. I'm from CSC Department of AML D section, and my course title is Web Systems Engineering, and the topic title is the Internet of Things in the Era of Generative AI, that vision and challenges. Now we can go through this. Introduction to IoT and Generative AI Convergence. The Internet of Things IoT connects billions of embedded devices via IP networks, generating massive heterogeneous data streams for real-time decision makings. And the generative AI models such as GANs and diffusion models synthesize high fidelity data, enabling simulation, anomaly detection, and predictive maintenance in IoT ecosystems. The convergence enables intelligent edge systems where generative models infer missing sensor data using variational autoencoders, that VAEs, and the federated learning frameworks allow distributed training of generative models across IoT nodes while preserving data privacy and minimizing bandwidth usage. And this synergy supports autonomous system adaptation, where AI driven digital twins evolve using generative feedback loops from physical IoT deployments. And this is the introduction to the IoT and generative AI convergences, that the Internet Things connects billions of embedded devices, and the generative AI models such as GANs and diffusion models, and they can predictive maintenance in IoT ecosystems, and it can federated learning frameworks allow distributed training of generative models across IoT nodes, and this energy supports autonomous systems adaptation. And now, next, the architectural foundations of AI integrated IoT systems. This is a modern IoT architectures follow a layered model that perception, sensors, and networks, that is communication, middleware, that is processing, and application layers. Each networks that AI modules. And the Edge AI integrates lightweight generative models, example tiny ML based diffusion networks, and the directly on resource constrained devices using quantization and pruning techniques. And next, the cloud edge orchestration uses Kubernetes based IoT platforms, that example KubeEdge, to deploy and scale generative AI workloads dynamically based on latency and compute demands. And next, the message queuing, telemetry transport, MQTT, and COAP protocols facilitate low overhead communication between IO devices and inference engines. And this is a digital twinning of the frameworks employ generative models to simulate the physical entities, updating state via Bayesian prototypes. And this is the architectural foundations of AI integrated IoT systems, that the modern IoT architectures follow a layered models that contains the communication, processing, and the Edge AI integrates lightweight generative models, and it can directly on resource constrained devices. And the cloud edge orchestration uses Kubernetes based IoT platforms. The message queuing, telemetry transport, and COAP protocols facilitate low overhead communication between IoT devices and AI inference engines. And the digital twin frameworks employ generative models to simulate the physical entities. And next, the generative AI models for IoT data synthesis, that variational autoencoders that reconstruct and generate synthetic sensors, the optimizing the evidence lower bound ELBOs, that mathematical lambda theta if I is equal to math BB, and this is a theory variations construction bound And next, the generative adversarial networks train generator and a discriminator D in minimax game. That minimum G max D V, that DAG equal to Mac baby, and the Mac baby equal to producing realistic IoT time series data. Diffusion models iteratively denoise data through forward and reverse Markov chains, enabling high fidelity generation of multimodal sensor inputs. The conditional GANs generate context aware data by conditioning on environmental variables, that example temperature, location, and it can improving simulation accuracy. Synthetic data generation reduces dependency on labeled datasets and crucial for training supervised models in sparse data IoT environments. These are the generative AI models for IoT data synthesis. And next, we can go through the edge intelligence and on device generative inference. The on device inference reduces latency and bandwidth by executing generatively directly on microcontrollers, example ESP32 and the Raspberry Pi, using TensorFlow by the microcontrollers. And next, the model compression techniques like pruning, quantization, example INT8, and knowledge distillation reduce model size and computational load for edge deployment. And next, the latency critical applications, example industrial robotics use real-time generative forecasting with auto-regressive models like a WaveNet or temporal fusion transformers. And next, the energy efficient inference is achieved via approximate computing and dynamic voltage frequency scaling tailored to generative workload patterns. And next, the hardware accelerators, example NPUs, TPUs, that can support parallel execution of matrix operation in generative neural networks and improving throughput on edge nodes. These are the edge intelligence and on-device generative inferences that can reduce the latency and bandwidth by executing generatives and the model compression techniques used with pruning and quantization. This can reduce model size and computational load for edge deployment. And these latency critical applications use real-time generative forecasting and the energy efficient inference is achieved via approximate computing and dynamic voltage frequencies. And next, federated learning for distributed generative AI in IoT. The federated learning enables collaborative training of generative models by decentralized IoT devices without centralizing raw data, preserving privacy. Clients compute local model updates that using stochastic gradient descent, which are aggregated server side via FedABG, and this is a formula for that. And that next, secure aggregation protocols, example homomorphic encryption, differential privacy, prevent leakage of sensitive gradients during model exchanges. And next, heterogeneous device capabilities require adaptive frequency learn federated learning strategies such as client clustering and asynchronous updates. So, to maintain convergence stability, generative models trained via FL can synthesize global data distributions while respecting local data constraints and enhancing cross device generalization. And next, digital twins and generative simulation. The digital twins are virtual replicas of physical IoT system that can continuously update the real-time sensor data and generative simulation models. The physical physics informed neural networks embed governing differential equations into the generative loss functions, and the generative models predict system degradation by simulating failure modes under the varying operation conditions. And next, the Monte Carlo based generative sampling evaluates system reliability under uncertainty. The computing matrices like mean time between failures the real-time synchronization between physical and digital entities use the Kalman filters for state transmission. And next, security and privacy challenges in AI-driven IoT. The adversarial attacks on generative models and the model inversion attacks reconstruct training data from the generative outputs that can threatening privacy in healthcare or smart home IoT deployments. And the secure multi-party computations enables privacy-preserving collaborative informations, and the blockchain-based audit trails ensure integrity of AI model updates and the data provenance in decentralized IoT networks. This is the security and privacy challenges in AI-driven IoT. And next, scalability and resource constraints in IoT AI systems. These are the resource constraints that IoT networks face scalability limits due to the constrained bandwidth, memory, and the generative AI exacerbates. And next, the hierarchical clustering of IoT devices reduces communication overhead by aggregating data at cluster heads, and the elastic scaling using serverless computing dynamically provisions cloud resources for bursty generative AI workloads. These are the scalability and resource constraints that are in AI IoT systems. And next, interoperability and standardization in AI IoT ecosystems. These are that lack of standardized data formats and one M2M and IEEE provide architectural for cross domains and the semantic ontologies like SAREF and the IoT Lite and the open APIs that are exposed generative AI capabilities. And next, standardized model exchange formats allow portable deploy of generative models across diverse hardware and software stacks. And next, the real world applications that smart cities and industrial IoT. That smart traffic systems use generative models to simulate urban mobility. And the next one is the generative AI forecasts energy demand in smart grids using LSTMs. And the industrial IoT that employs generative anomaly detection to identify equipment through falls from vibration and thermal sensor data using autoencoders, and the smart buildings leverages generative models to synthesize occupancy patterns, and it can enabling adapting HVAC control and energy efficiency optimization. These are the real world applications that smart cities and industrial IoT apply. And the real world applications where the healthcare and agriculture will be applicable, that wearable IoT devices uses generative models to impute the missing physiologicals, and it can precision agriculture employs drone based IoT sensors and generative models to predict crop yields and detect pests using multispectral image synthesis. And the autonomous irrigation systems use generative reinforcement learning to optimize water usage based on predicted weather and the what about the growth models. These are the applications in real world. And this is the emerging research directions and open problems that are neurosymbolic integrations, and the continual learning enables generative models to adapt to evolving IoT environments, and the casual generative models in for intervention effects, and the quantum inspired generative algorithms, and the ethical AI frameworks are needed to govern autonomous generative decisions in life critical IoT applications that are ensuring fairness and accountability. And conclusion about this is the vision of autonomous intelligent IoT ecosystems, that the fusion of IoT and generative AI enables self-configuring, self-healing and optimizing systems capable of autonomous operation in dynamic environments. And the future IoT ecosystems will rely on closed loop control where generative models predict, simulate and act upon physical world challenges in real time. And this can advances in edge AI, federated learning, and digital twins will drive the next generation of intelligent infrastructure across industries. And this convergence represents a paradigm shift toward ambient intelligence where AI seamlessly integrates into the fabric of everyday connected systems. Thank you.